Hi, everybody. This time we're going to talk about specific heat. Now, you know that different substances absorb and release heat differently. The scientific name for that is specific heat. And one of my favorite foods is pizza. And one of the classic questions is which part of the pizza actually burns your mouth? Is it the cheese, the sauce, the crust, or all the lovely toppings? Well, we're going to revisit this question at the end after you know a little bit more about specific heat. Specific heat is defined as the energy needed to increase the temperature of 1 kilogram of substance by 1 degree Celsius, or the temperature needed to raise the temperature of 1 gram of substance by 1 degree Celsius. One of my most interesting observations is very often I'll take a lasagna out of the oven and I'll use my hot pads, and because it's a hot oven, and I'll have my nice little hot pads and I'll protect my hands, and I'll take the lasagna, I'll set it on the kitchen counter, then I'll take my hot pads off, and with my naked little fingers I'll peel off the aluminum foil. And it's like, how do you do that? Why can you get away with that? Well, that's because of specific heat, because of the fact that the water molecules, the steam from the water that's coming up from lasagna, has a very, very high specific heat, meaning it holds a lot of energy in every single molecule. But aluminum has a relatively low specific heat, and that means it cools down quickly and it heats up quickly. The definition of 1 calorie is actually defined as the amount of heat necessary to raise 1 gram of water 1 degree Celsius hotter. And that is actually a definition of the specific heat of water. So this all is kind of wrapped up together. Back when we were talking about the periodic table and we were talking about properties of metals and nonmetals, all the lovely metals on our left side of the periodic table over here have low specific heats. They heat up quickly, they cool down quickly. And what that means is we use them in situations where we want to remove heat from a situation. We use them in refrigeration units, we use them in furnaces, we use them in CPU units and power supplies in computers when we want to suck heat away. We use them in cooking pans, mostly because we want the heat to go through the pan into the lovely food. Metals have this wonderful metallic bond, and if you remember that crazy metallic bond, what happens is these metal atoms are living in this kind of hippie commune. And these metal atoms are kind of loosey-goosey, held together. The electrons are free to wiggle and move around them. And that freedom allows kinetic energy to move. Well, heat is a lot of motion. And motion is kinetic energy. And if these electrons can move, heat can move through the material very, very easily. So it's this loosey-goosey arrangement of electrons that allows the heat to move through the metals quickly, and that gives them this low specific heat. Non-metallic substances up in this upper right portion of our periodic table and our friend hydrogen, these things have covalent bonds. And covalent bonds, as you know, involve sharing electrons. Now, if you share electrons, they are trapped between the carbons and the hydrogens, between the hydrogens and the oxygens. They are trapped in something that is stuck. And because they are stuck, these electrons are not going to move. You have no motion. And when you have no motion, you can have no kinetic energy. And there's no motion, there's no kinetic energy, and there's not going to be heat that will be transported. So if we look at things that are good insulators, we have carbon and hydrogen compounds in styrofoam. We have silicon and oxygen compounds in fiberglass. Air is a wonderful insulator. Well, air is oxygen and nitrogen. These are all non-metallic things, covalently bonded. We wear fuzzy, wuzzy, air-trapping things in the winter when it's really cold. Combination of oxygen-nitrogen trapping for our air, plus they're made of carbon and hydrogen compounds. So this non-metallic, covalently bonded things are great high specific heats. Insulators, heat does not transfer well, and that's due to that covalent bond. Now, water is special. Water is special because it has a crazy high specific heat. Let's look at this. Water has a specific heat. On my little chart here, it is the highest of everything. It is twice as big as ice and steam, and much bigger than these metals down here like copper, silver, gold. Why does water have a high specific heat? Two reasons. One, when you've got H2O and you've got hydrogen, two hydrogens bonded to an oxygen, that is a nice, strong covalent bond. But the other part of it that makes liquid water even a better high specific heat thing than ice and steam is the fact that water is a polar molecule. It has two unbonded electron pairs out in the front of the oxygen, making the front end of it a little negative. The back end is a little bit positive, and water molecules in a liquid state tend to line up positive to negative, positive to negative. And this extra attraction, this extra electrical attraction, positive to negative, negative to positive, makes water bonded to itself very, very strong. And that means that it does not want to move, and you have to put in a massive amount of heat to get water molecule to change into ice or into steam. That means a very high specific heat. Because of that, we use it in cooling systems. The most important cooling system, of course, the human body. When we think about perspiration, we have to take heat, our bodies have to take heat from body temperature, somewhere around 37 Celsius. It removes heat, getting it up to that vaporization temperature, that latent heat of vaporization, and all of this heat is removed from our body when water evaporates off our skin. Because of this high specific heat, it's great in car radiators. It is great in home radiators. It is great in cooling systems in power plants. And it's not just because water is abundant and cheap, it's also because it is a fabulous coolant because of that high specific heat. Because of this high specific heat, water heating appliances tend to be very expensive to run. Take a look at this little chart that has to do with wattages of common appliances. If you look at a water heater, if you have an electric water heater, crazy high wattage. Why? It's because water is bonded to itself very, very tightly. And if you want to add kinetic energy to those water molecules, you have to put in a massive amount of energy. Well, my friends, when you pay your electric bill, you pay for energy. And so I give you permission to yell at your family members if they're wasting energy, because they waste energy, they're wasting money. Now, look also at the clothes dryer. The clothes dryer, also really expensive to operate. Why? Go back to that latent heat graph we talked about last talk. Because we've got to take your wet clothes and take that water from room temperature, get it up to boiling temperature, and then we've got to vaporize that water out of your clothes. It takes massive amounts of energy to do that. Anytime you've got to mess with those water molecules, you got to put in a lot of energy, and you pay for energy. Water's high specific heat also impacts climate. When a part of the earth is close to an ocean, oceans tend to absorb heat all summer, and then they slowly release that heat all winter. Let's take a look at something. Where I live is in Wisconsin, right about there, right between hardness zone 3 and 4. Now, hardness zone is what is used by gardeners to determine if a plant's going to live if you plant it there. Now, what this means is the coldest temperatures in the area where I live get to about 30, sometimes minus 40 degrees Fahrenheit. But if you go to the similar latitude, you go straight west, you are in Oregon and Washington in the Pacific Northwest. In the Pacific Northwest, these areas up here have low winter temperatures. They almost never get below 10 degrees Fahrenheit. How come if you get the same amount of sunshine and at the same latitude, you're getting the same amount of light from the sun, how come they can be so much warmer in the wintertime? And it's due to the beautiful Pacific Ocean. The Pacific Ocean is absorbing heat all summer, releasing that heat all winter, and it's due to water's very high specific heat. I went to school in England for a period of time during college, and when I was in college, I was amazed at the fact that the climate was so incredibly mild, specifically looking at the fact that the latitude was really, really high, way up there next to Hudson Bay in northern Canada. Now, if we were in North America, we'd be way up here and it would be 40, 50 below Fahrenheit in a winter day. But you watch the Harry Potter movies and Harry and Hermione are running around in little wool coats. They're not acting like it's that cold. And that's because of the fact that England is an island and it's surrounded by water. This water that England is surrounded by also has currents that bring the water up from the Caribbean to those islands that make England very mild and Ireland the Emerald Isle. This is a hardness map for the British Isles, and some areas have a hardness zone of 10. What does that mean? That means it never freezes. There are parts of southwestern England that never ever freezes, and actually in England there are in some areas palm trees that never freeze, and it feels wacky. They can be so far north and have palm trees, but it's due to water's high specific heat, and it's due to those amazing intermolecular forces of the water molecule. Hawaii is another place that's amazing. It's surrounded by water, and because it's surrounded by water, their temperatures are very, very consistent. Seldom change between, they'd seldom get very cold or very warm. Why? Water, that temperateness of water. So let's go back to our friend pizza. So what part of the pizza is going to burn you? Probably the sauce. The crust isn't going to do it, and I don't know about you, but my green peppers are usually not my enemy when I'm eating pizza. I like green peppers. It's going to be that hot, hot sauce. All right, have a good one. Enjoy your pizza. We'll see you soon. Bye-bye.